Hey everybody, let's look at some specific examples of the three-part continuity test. All right, pardon my rough sketch here. All right, so you should have a worksheet that looks similar to this. This is the second part of the continuity notes, and so it's notes 1-9. All right, so we have the same piecewise function. Now we're looking at not limits at the integers, but we're kind of studying the continuity topic here. Using our graph as a visual to assist us in answering the questions about continuity. I'm going to pick on the integers again. Like I said, I could pick on any number. I just decided it's just easier to work with the integers. So let's say you're given this graph and you're asked to verify, show, prove that this graph is continuous at x equals 0, okay, or not continuous. All right, using the three-part continuity test. So have those notes handy right next to you so you can refer back to them if need be, and certainly pause the video if you need to at different times. All right, I'm asking you, is this graph continuous at x equals 0? And as you look at it, notice that there's no part of the graph to the left of x equals 0. Okay, well, that's okay. That's okay. A graph can still be continuous without having graph on either side of it. So let's look at the three-part continuity test. So first test, is there a functional value at 0? Just like we saw f of c. But is there a functional value at 0? Sure, it's 1. So the function exists at 0 and it's 1. Okay, let's move on. It's all looking good. All right, let's look at the second part. Does the limit exist as I approach 0 from both the left and the right? Well, notice there's no graph to the left, so there's no conflict here. I don't need to worry about a jump discontinuity if I don't have a graph to the left of x equals 0. So, I mean, in this case, all I really have is what we call a right-hand limit to consider. And certainly the limit exists from the right. So the limit as x approaches 0 from the right. It would be okay to leave off the positive sign to indicate from the right only. That's certainly fine. We would just know that there's no graph to the left. So as I approach 0 from the right, I am on the first piece of the function. I'm getting closer to 0 as indicated over here by the inequality. I could just put down f of x, but I'm just going to go ahead and practice using the correct piece. All right, does the limit exist? Well, plug in 0, evaluate, we get 1. Okay, that's the limit. It is only a right-hand limit, but it is the limit of the function as x approaches 0, and it's fine. Okay, third part of the continuity test says, does the functional value in part 1 equal the limit value in part 2? Simply, does 1 equal 1? It does. So what's the notation that we should show? Well, to verify continuity, f of 0, the functional value, which is 1, that's what this is equal to the limit statement. Because if these are both equal to 1, I can equate these two statements. I'm leaving off the superscript. It's perfectly fine. I could put in negative x plus 1, but here I'm just going to put in the generic name. So I'm just going to do the symbols. Therefore, f is continuous at x equals 0. Kind of abbreviating there. Okay. As you travel across this graph from 0 to 1, you can see that the graph is continuous everywhere between 0 and 1. So that's not a big concern for us. Let's move on and let's look at the next integer. That's at. Let's apply the three-part continuity test. Same question. Is the graph continuous at x equals 1? A quick inspection shows no, the graph's not continuous at x equals 1. Why? We have a jump discontinuity. So using the three-part continuity test, first of all, does the function exist at 1? Well, let me see. Here's 1. If I looked up or looked down, I can see that there is a point there. There's a y value belonging to that x. So yes, the function is defined. The function exists there. Okay, part 2. Does the left limit equal the right limit? Well, clearly no. We see that it doesn't. So the three-part continuity test is already going to fail in part 2. There's no sense in even going to part 3, but let's show that. the left limit. If I approach 1 from the left, that's smaller values than 1, so I'm still on this linear piece, which that makes sense. I'm coming down this part of the graph. Negative x plus 1. Plug in 1, negative 1 plus, that's a plus. Plus 1 is 0. All right, so the left limit is 0. The y values are going to 0. Makes sense. Let's see where this is going. I'm looking at the right limit. Okay, if I looked at the right limit here, I'm approaching 1 from the right. Well, if I approach 1 from the right, I'm on this piece. I'm on the horizontal piece right here. So those y values are 1. Let's see. Okay. There. So there we go. We can clearly see that 0 does not equal 1. That is numerically the support of this jump discontinuity. So therefore, the limit does not exist. And notice I'm going to go to just general function notation because both sides of 1 require 2 different pieces here. So just using 1 to capture the function. Equals does not exist. Therefore, I guess again, f is not continuous at x equals 1. F is not continuous at x equals 1. All right, let's try at x equals 2. Okay, we'll just look quickly at the graph. If I didn't have a graph and just was given the piecewise equation right here, well, then I really wouldn't have something to support my answer with. That's fine, but it sure is nice to have an idea what the answer should be before we actually go in and calculate it. I'm standing here at x equals 2. While I'm trying to draw the graph, I can see that this is a removable discontinuity. That I would have to jump up here and draw the graph. So no, the graph's not continuous. I'm going to have to show that the graph is not continuous at x equals 2, and I'm sure one part of these 3 parts right here is going to fail. So part 1. Does the function exist at 2? There's 2. Go up. Yep, the y value is 2. Okay, does the limit exist as x approaches 2? Well, hopefully based on our previous work, you guys can see that the limit does exist, that the left limit and the right limit are both equal. If I approach 2 from the left, I'm certainly on this piece, and this piece corresponds to this piece in the piecewise graph, so the left limit is 1. I'm still a little colon here, save some space. Semicolon. As I approach 2 from the right, okay, I don't want to be at x equals 2. That's the functional value, so I'm jumping down here to this piece. 2 from the right would put me in this interval, so I'm on the piece x minus 1. Substitute in, I get 1. Okay, we see that the left limit equals the right limit, so therefore, the limit as x approaches 2 of the function is equal to 1. That's nice, good. The function exists, the limit exists. Okay, the problem here is this. That value 2 does not equal that value 1. F of 2 does not equal the limit of the function as x approaches 2. And that just shares or verifies that, we have that removable discontinuity in there. All right, this might be a good time for you guys to go ahead and, look at the continuity. Right. Yeah, so this might be a good time for you guys to maybe attempt to verify, prove continuity, or disprove continuity. At this point, we're just going to use the 3-part continuity test at the integer x equals 3 and x equals 4. So this might be a good time for you to pause the video, attempt it on your own, and then come back and look at it and see how you did. All right, so you may well have proven that f is continuous at x equals 3, and f is also continuous at x equals 4. The graph verifies that you don't have to lift up your pencil as you travel through x equals 3. The functional value equals the limit value, and all works well here. Okay, let's look at x equals 4, because that's kind of like the case up here when we looked at the integer at x equals 0, meaning the function exists. We only have a left-hand limit. So it's okay if you don't have that superscript, just like up here, it's okay if you don't have that superscript. But if you do put one, it's only from the left for this part. There's no graph to the right of x equals 4. That's just the way the piecewise function was defined. Okay, we see that the functional value equals the limit value. Notice I dropped the superscript. With or without it, doesn't matter. Therefore, f is continuous at x equals 4. And before I kind of close, I want to look back up here. I think I didn't put down the result here that at x equals 2, f is not continuous. So let me do that right now. F is not continuous at x equals 2. We failed the third part of the three-part continuity test. Okay, so hopefully you have a better understanding of continuity. Hopefully with this practice, you understand the three-part continuity test. Okay, I'll see you soon.